Great. Okay. So these are these two curves of a temperature proxy. You know, we don't have a direct temperature measurement, obviously, all that time back, but this is a temperature proxy based on some isotopic composition of the ice in the ice cores. We talked about that in the first class. Okay. So this brings us to a concept called radiative forcing. So radiative forcing is the effect of CO2. It's basically how much heat is being trapped by the CO2 in watts per meter square. The more technical definition is this. You increase the CO2 abruptly, and then you allow the stratospheric temperature, so above 8 to 10 kilometers or 12 kilometers or so, to readjust to the higher CO2. And then you check how the radiation changes at the top of the troposphere, at the tropopause, to see how much less heat is escaping. Okay, so before the temperature adjusted, after changing the CO2, how much is the escaping heat changing? And the less that is escaping, the higher the radiative forcing. In terms of a graph, what this looks like, it's this. So you can see the curve for the CO2. So you can see that the radiative forcing due to the CO2 is reaching right now more than 1.5 watts per meter square. That's the increase until pretty much now, or a bit 10 years ago maybe. Okay. So the question is, why is this increase in CO2 causing the radiative forcing? Why is it trapping the heat, and what is the effect of that trapping? So now this is the radiative forcing for different scenarios. We don't know how CO2 will rise in the future. So people came up with a few scenarios. There's RCP 8.5 means that by 2100, the radiative forcing would be 8.5 watts per meter square. While there are more optimistic scenarios, 2.6, 4.5, and so on. And you could see the curves of the radiative forcing as function of time in all of these. Which one will be selected depends on what action is taken, obviously, in terms of emissions and so on. Okay, so these are the questions that we're going to try and address today. How do these greenhouse gases warm the planet? How can such a small change in CO2, if you remember the Skeptic movie that we saw in the first class, they talked about CO2 being a very small fraction, only 0.04% by volume. Right now, how can such a small change make a difference, such a big difference? What is the quantitative relation between CO2 and radiative forcing and temperature? What about other greenhouse gases? What about water vapor? People tell us that water vapor is the most important greenhouse gas, which it is. Is that a reason to worry less or more? Turns out more. So why don't we start with this first workshop in which you plot the observed and projected increase in greenhouse gases. Okay, why don't we move on in that case? So you plotted one scenario, I think. These are all of the scenarios. So that's the worst case scenario, and then the other ones. This is the projection. This is where we are right now. So this is a projection made a few years ago, and so far we're doing very well. We're exactly on the red curve of worst case scenario. Okay? So that's the good news. Now let's see how the warming is explained by all of this. Okay, now we're coming to the question of why would this affect the temperature? So we start with the concept of an energy balance model. So here's the idea. This is the Earth's surface, the atmosphere above it. You have the incoming radiation from the sun, which is on average over the globe in a day, about 300 and something watts per meter square. Some of this is reflected by clouds, some of this is reflected by the surface, and some of it is absorbed. So about 168 watts per meter square is absorbed by the surface. Okay? Now, interestingly enough, there is this exchange here between the atmosphere and the surface that is basically twice as big as this radiation coming from the sun. This is the greenhouse effect. So the surface is being heated by the incoming solar radiation. Some of this is absorbed back up as long wave radiation. That is heat, basically. We'll see why it's called long wave radiation in a second. It's absorbed by the atmosphere, and the atmosphere sends it back down. And then the atmosphere also emits some radiation, some heat upward. So this is the natural greenhouse effect. Before we even get to anthropogenic increase in CO2, this is the effect of having an atmosphere and how it affects the energy balance of the surface. It's basically these two large fluxes that are being exchanged by the surface and the atmosphere. Any questions about any of that so far? So is the concept clear that the Earth is absorbing sunlight and then it's releasing heat, and that heat is absorbed by the atmosphere and sent back and then also up? Let's see how we represent this mathematically in order to see how much heat, how the temperature is affected by this greenhouse effect. And then we'll get into the anthropogenic greenhouse effect, which is a slightly different story. So suppose first we didn't have any atmosphere. Then the situation is pretty simple. Here's the surface. We have an incoming radiation from the sun. Some of it is being reflected. Okay. And then the surface itself is emitting heat. So that's also electromagnetic radiation. And we need to balance what's absorbed with what is outgoing. So the first step is how much is coming from the sun. Let's figure that out first. So suppose this is the sun. This is the Earth. And I drew a cross section of the Earth here. So this is half an Earth, basically. The sun is emitting something that's about 1361 watts per meter square. So 1300 roughly. And the question is how much is absorbed by this cross section that the sun sees. So if the radius of the Earth is r, then what's absorbed is, let's call this S0. What's absorbed is S0 times pi r squared, the area of this cross section. Okay? Now this absorbed heat is distributed over the surface of the Earth. What is the surface of a sphere? Surface area of a sphere? Okay, so we need to divide that by the area, and the area is 4 pi r squared. So this becomes S0 divided by 4. So this is the radiation absorbed on average over a day where the entire surface is exposed to the sun. We have S0 divided by 4. So what's incoming is S0 divided by 4. What's reflected is a fraction alpha times that. So that would be here. What we have is alpha times S0 divided by 4. And what's absorbed here, therefore, is 1 minus alpha S0 divided by 4. So now we know what is the input. What about the output? Okay, so the Earth has some temperature. And the outgoing radiation is going to be sigma T to the fourth, where this is the surface temperature. And sigma is the Stefan-Boltzmann constant. So now the energy balance of the Earth simply tells us that what's incoming is equal to what's outgoing, so that the things are in equilibrium. So income is equal to outgoing. And that means that we have S0 divided by 4, 1 minus alpha, is equal to sigma T to the fourth. So therefore the temperature is equal to, divide by sigma here, S0 divided by 4, 1 minus alpha, all of that to the power of 1/4. And if we substitute numbers for alpha, sigma, S0, and so on, this ends up being about 255 Kelvin, which is roughly minus 18 Celsius. What is the average temperature of the surface of the Earth? Does anyone know? Yeah, something like 14 degrees maybe. So we're very far from that, and if that were the temperature of the Earth, we would be in a very, very bad shape. So what's missing here is the natural greenhouse effect of the atmosphere. So let's try to represent that and see how the greenhouse effect of the atmosphere warms the surface and allows us to be around. So let's add the atmosphere now. So how do we do that? Well, we have to change the picture a little bit now. So we have, now we still have the surface, so with an atmosphere. We have a surface, sun here. Now we have an atmospheric layer. So the sun is sending us again the S0 divided by 4, just like before. Some of this is being reflected. This would be the alpha times S0 divided by 4, just like before. The surface is emitting heat at a temperature T. The atmosphere now also has a temperature, which is TA, T atmosphere. So this radiation in this picture is now absorbed by the atmosphere and is sent back. So when the atmosphere sends back this radiation, what's going to be sent back is sigma T atmosphere to the fourth. And then it's also sending radiation up, heat up. And that would be also sigma TA to the fourth. And now we drew all the fluxes, and we can write the input equal output balance for this new picture. Yes? Yeah.
Why is the ground radiation just T and not sigma T to the fourth?
No, the radiation by this is sigma T to the fourth. T is the temperature. Okay, so now we need to write an input equal output equation for each of these two places. One is the surface and one is the atmosphere. So let's do this. So energy balance for the surface. So that would be, let's see, we have 1 minus alpha times S0 divided by 4. That's just like before. This is the radiation coming from the sun. But this time we also have this part. So plus sigma T atmosphere to the fourth. And what the surface is losing is sigma T to the fourth. Now we mentioned that a body with a temperature T, if it is a black body, will emit sigma T to the fourth. The thing is that a black body is a perfect black body is one that absorbs all the radiation that is emitted toward it, but the atmosphere and the surface are not exactly perfect black bodies, especially the atmosphere. So we need to correct it, and we're going to put an epsilon here. This epsilon is referred to as the emissivity. That emissivity is an order 1 constant, like 0.7, 0.8, that takes into account the fact that the Earth is not a perfect, that the atmosphere is not a perfect black body, but emits at a slightly lower efficiency. Okay. And now we want to do the same thing for the atmosphere. So energy balance for the atmosphere. So let's see, what is the atmosphere absorbing? It's absorbing what's coming from the surface. So sigma T to the fourth is going to be equal to 2 times sigma TA to the fourth, because the atmosphere layer, the atmospheric layer is assumed to be emitting both up and down. Okay, so now we have two equations with two unknowns. The two unknowns are T and TA, and we can solve for both. And we need to put in the epsilons in this case. So we know that the emission by the atmosphere is corrected by this epsilon here. The absorption is corrected by the same factor, so we need to have an epsilon here as well. This is the fraction of the radiation emitted by the surface that is absorbed by the atmosphere. It's not all of this flux, it's only that times epsilon, because the atmosphere is not a perfect black body, so it doesn't absorb everything and it doesn't emit exactly like a black body. Okay, so two equations with two unknowns. We substitute the second one into the first one. So substitute 2 into 1. And we get a solution that looks like this. T is equal to S0 divided by 4, 1 minus alpha, divided by sigma, 1 minus epsilon over 2. All of that to the power of 1 over 4. If we call the previous solution that we found T0, the one with no atmosphere, then we can write this as T0 times 1 minus epsilon divided by 2 to the power of 1 over 4, minus 1 over 4. And this number is now 284 Kelvin, which is roughly 13 Celsius. And that's much closer to the actual temperature of the surface. So we now explained why the Earth is not at minus 18 Celsius, but instead at 13 or 14 Celsius. And it's all the effect of the absorption by the atmosphere, which we've added now.
T naught here?
T naught is the solution we had before, right here. I'm calling this thing T naught. T naught is the solution with no atmosphere. And this is the solution with an atmosphere expressed in terms of the previous solution. So you see the factor between them is 1 minus epsilon divided by 2 to the power of 1 over 4. We think of the atmosphere as being a layer. This layer has an upper surface and a lower surface. Each of them is emitting a long-wave radiation heat at the rate of epsilon sigma Ta to the fourth. Two separate surfaces that are emitting in both directions, yes. We talked about long-wave radiation and short-wave radiation. Let me explain what that is all about. The radiation emitted by the sun as function of the wavelength, the electromagnetic wavelength, and then the radiation emitted by the Earth as function of wavelength. And you simply see, first of all, of course, the amplitude of that, which is the red axis here, is much larger than the amplitude of this because the sun is much hotter and emits much more radiation. But also, you see that the wavelength of the radiation is shorter than the wavelength of this radiation. So we therefore refer to the incoming radiation from the sun as shortwave, and the outgoing radiation that is emitted by the Earth, the heat that is emitted by the Earth, as longwave. Okay? So this is what we did so far. This is with the atmospheric layer. And now we're coming to the question of what happens when we are adding CO2, anthropogenic CO2. So we're going to have three pictures here. This one is before adding any CO2. This one will be right after adding CO2, before the temperature has time to change. So we're assuming an abrupt emission, say abrupt doubling of CO2, before the temperature had time to change. And this one will be what happens after the temperature adjusts to the new CO2. So we'll try to understand this in three steps. So the new element, we're adding two new elements here. One is the fact that atmospheric temperature varies as function of height and decreasing in what's known as the lapse rate, right? Lapse rate is the rate at which the temperature goes down. What is the rate at which the atmosphere goes down as you go up? Say 5 to 10 degrees Kelvin per kilometer, right? Depending. Okay. So that's this green line. It's the temperature as function of height. Make sense? Okay, that's one new element we're putting in. The second new element is the emission height. This is this height here. The idea is the following. You have heat is escaping from the surface, is released by the surface, and it's absorbed by the atmosphere at some height. And then it's released again and absorbed again, and then it's released again and absorbed again. At some point, these photons of heat, heat is an electromagnetic radiation, so it's photons. These photons are likely to escape to outer space because the atmosphere above that height is sufficiently thin that the photons are likely to escape completely to outer space. So we call that height, the emission height. So if we're sitting outside in outer space and we're looking down, we're seeing radiation that was emitted from the emission height in the atmosphere and not from the surface. Okay? So let's see. So at the top of the atmosphere, what we have is the incoming radiation minus the part that was reflected. This is the sunlight, is equal to the long wave radiation from the emission height. Below the emission height, we have the balance that we just described of the surface receiving radiation from the atmosphere and also receiving radiation from the sun. Okay? Suppose now that we increase the CO2, what happens? So you look at this right here, and you see that the emission height went up right here. And the reason is this. So it used to be that photons emitted from this level are able to escape to outer space, but we've added CO2. CO2 traps these photons. So some of these photons that were able to escape before are trapped again and then released again. So the effective emission height has increased to this point right here. Okay? So this is the result of us increasing the CO2 and allowing some of these photons that used to be able to escape to be trapped again. Okay. Now, what happens as a result of that is this. Remember, the atmospheric temperature is going down with height, so the new emission temperature, this point right here, is the temperature at the new emission height. So the radiation emitted by that, which is sigma T atmosphere to the fourth, is smaller than the radiation emitted at this previous emission height. So less radiation is emitted from the new emission height to outer space than before. Right? Again, this temperature here at the new emission height is smaller than the temperature at the old emission height, and therefore sigma TA to the fourth is smaller. And as a result of that, short wave, which is the radiation coming from the sun, is larger than long wave, which is the radiation released from the emission height. So now we have a situation in which more radiation is coming in than is going out, and that necessarily implies warming until the system re-equilibrates. Okay, so then, this happened immediately. The CO2 was doubled instantaneously, and now we give the system a long time, 1,000 years or whichever, to equilibrate, and this is the new situation. So because there was more incoming radiation than outgoing radiation, the atmosphere and the ocean warmed, and so the temperature profile moved from here to here. So the dashed line is the old temperature profile, the green solid line is the new temperature. And if you look at this carefully, you see that even though the emission height is still higher, because of the warming, the temperature at the new emission height, the new temperature at the new emission height is equal to the old temperature at the previous emission height. So that is, see this point right here, the temperature points to this circle right here, which is the same circle here. Okay? Now, what this means is that the radiation emitted by this new emission height is sigma T to the fourth is equal to the original one right here. So now the incoming radiation, which we refer to as shortwave, we'll see again soon why, is equal to so this is the received radiation from the sun. The shortwave is equal to the emitted radiation long wave, and we're in equilibrium again, and the atmosphere doesn't warm anymore. So two things happened. One, the emission height increased, and two, the temperature warmed. As a result of that, the temperature at the emission height now, after the adjustment of the temperature, is as high as it was in the old emission height. In fact, the shift is not as plotted here because there's actually a change in the slope as it shifts. We'll talk about that later in the course. Right now, just for simplicity, I'm assuming that the shift occurs in parallel, but that's actually not correct. We were here, and most photons were able to escape to outer space. Now we've added CO2. CO2 is a well-mixed gas. That is, there's more of it everywhere, including above the emission height. So some of these photons that used to be able to escape from here are trapped by the new CO2 molecules that we've added here. And therefore, the new emission height from which most photons can escape is a bit higher now. Make sense? I guess an important point to understand here is the following. CO2 absorbs in a certain wavelength of radiation. Again, something we'll talk about soon. So the point is that every photon of heat that is escaping from the surface, even without raising the CO2, would have been absorbed by the atmosphere and not be able to escape to outer space. So it's not about trapping more of these photons by CO2. It's about trapping them higher in the atmosphere. Does that make sense? That's a really important point, so I want to say it again, okay? Here's the idea. Every photon of heat that is escaping from the surface would have been trapped by the atmosphere even without us increasing the CO2, because there's enough CO2 to do that. The thing is that now, instead of being trapped all the way to this emission height, it's now trapped to this emission height where the temperature is colder, and that allows this incoming radiation to be larger than the outgoing radiation, and that causes the warming. Okay, so now you can move to the next workshop, which is this two-level energy balance model, and try to understand how it works in more details and substitute the numbers yourself and so on. So what we're doing now is how greenhouse gases work. Why is it that CO2 actually traps these heat photons, right? And it's all based on the idea that white sunlight is made of different colors, different wavelength if you want, and then different molecules absorb different wavelengths, and we want to understand why. So first of all, black body radiation. We talked about the black body. Black body is a body at a certain temperature which absorbs all the radiation that is thrown at it and is emitting according to this law. This is the wavelength of the radiation being emitted, and this is the temperature of the black body. So the radiation is a function of both, and you can see B is the energy per area, per unit time, per angle emitted from the surface of this black body between the wavelengths of lambda and d lambda, and lambda plus d lambda at a temperature T. Okay, never mind the formula. This is what it looks like for different temperatures. And if you integrate this over all wavelengths, all lambdas, you get that the total is sigma 2 to the fourth, which we've used already before. Okay, so the total radiation is sigma t to the fourth. The radiation at each wavelength is given by these curves. So we saw the one on the left already. So this is the shortwave radiation coming from the sun. This is the outgoing long-wave radiation. This is what actually this is an estimate of what it actually looks like at the top of the atmosphere. So this curve right here is the black body radiation curve for 287 Kelvin, which is roughly the average temperature of the Earth. And you see that there's some holes there. And these holes are because of the greenhouse gases. So what this tells us is at this place there's a hole because there's CO2 in the atmosphere, and the CO2 absorbs radiation at this range of wavelengths. Why, we'll see in a second. And then there's also a place where O3, ozone, is absorbing, and CO4 and water vapor here too. Water vapor is playing an important role in this, as you can see, but you could also see that CO2 is playing an important role. Okay? And because of this difference between shortwave radiation and longwave radiation, we refer to the sunlight as shortwave and the escaping radiation from the Earth as longwave. A short video on how greenhouse gases actually work, and then, as usual, we'll go over it carefully, but let's watch it first.
In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around.
So here's the idea. It's simple. If you have electromagnetic radiation, in order to interact with something, that something needs to have a charge. These molecules don't have charge, and net charge, because there's an equal number of electrons and protons. So there's no net charge. However, they do tend to keep some of the electrons on one side and some of the positive charge on the other side. So it actually looks like this. So this would be a water molecule, and you can see that it's positively charged here and negatively charged here. So even though the net charge is zero, an electromagnetic radiation seeing this molecule will see positive and negative charge, and it can interact with it. By interact, we mean that it can be absorbed by the molecule. And when it's absorbed, what happens is that you start getting vibrations. So for example, the arms of the molecule could start vibrating or getting shorter and longer and so on and so forth. That's what happens when a long wave radiation photon is absorbed by this molecule. What about CO2? So this is water, and it has this naturally occurring charge distribution. CO2 is a bit different. So here's CO2. When it's not vibrating, there's no charge, there's no excess charge anywhere, but when it starts vibrating, it develops this charge excess on this side and that side, and then it looks more like the water molecule that we saw before, and now it can interact with the radiation and it can absorb these long wave photons that further excite these vibrations. Here's the picture again, these molecules vibrating, and now because this is a quantum system, here's the important thing to understand. Let me turn the light on. Okay, so there's going to be this would be energy of a molecule, okay? And there's going to be some base level when it's not vibrating. And then the vibrations can take any energy. Because it's a quantum system, there's going to be a certain discrete levels of energy that correspond to different vibrations. Okay? So if it's vibration strongly, we would be at a high energy level. If it vibrates weakly, there would be a low one. When a photon is absorbed, we can transition between two energy levels. For example, we could jump from here to here, or we could jump from here to here. So there are many levels and many such transitions. Okay? And then when a photon is released by these vibrations, we go back. We could go back from here to here, we could go back from here to here, and so on. So there are many transitions, so many wavelengths of photons that can be absorbed, but these are discrete levels of energy of photons that must be exactly at the right energy level. What is the energy of a photon? It's going to be h times n, where n is the frequency of the photon, and h is an appropriate constant. And so the frequency of the photon, or if you want the wavelength of the photon, wavelength and frequency are related, right? Has to be exactly at the right value in order for the energy of the photon to be exactly the difference between two energy levels of the molecule. Okay?
Can you explain that formula again?
Right. This is the energy of a photon, and n is the frequency of the photon. So the energy of a photon is equal to h n. And what is the relation between frequency and wavelength? So tell me, what should I be writing?
The wavelength equals c over the frequency.
Right, where c is the, okay, so the wavelength of the photon is given by the speed of light divided by the frequency. So if the frequency needs to have a certain value for the photon energy to be in a certain range so that it exactly allows a molecule to move from one energy to the next, the wavelength also needs to be in a very specific range in order to allow that to happen.
So is this trying to explain how like certain wavelengths can pass through the atmosphere when other wavelengths can't?
Exactly, yeah. Yeah, so CO2 happens to have energy levels. Remember, these energy levels correspond to different vibration modes of the CO2. And the difference between the energy levels of the CO2 molecule exactly corresponds to the wavelength of incoming radiation from the surface that is absorbed by the CO2 molecules. Great. You can see that because there are many levels, there are also going to be many such transitions between them. So the more levels, the more possible transitions. We'll see that in a second. So now, here is a plot. Each of these peaks corresponds to a wavelength, or wave number in this case, 1 over the wavelength, at which the CO2 molecule can absorb. Okay? Now, this is a very small range of wave numbers, wavelength. If I look at the full range, the picture looks like this. So because because there are many levels, there are going to be many, many peaks. And when you look at the peaks, they actually form this continuum. All of this continuum explains the hole in the outgoing long-wave radiation that we saw before. Let me remind you. So we saw this hole before, right here. This absorption by CO2 corresponds to the frequencies of photons that allow the CO2 to transition between two vibration modes, energy levels. You could think of this as a coincidence that CO2 molecules happen to do that. And so do the other greenhouse gases, the methane and others. Although CO2 has very specific absorption lines, these are the absorption lines, it turns out that CO2 molecules, as well as methane, as well as water vapor molecules, can actually absorb photons that don't exactly have the right frequency due to two what's known as broadening mechanisms. Broadening stands for the fact that even though there's a certain frequency or wavelength that can be absorbed, the peak of absorption can be wider due to these two effects that I'm about to cover. Okay, now that's very important because this allows CO2 and water vapor to be more effective as greenhouse gases and absorb frequencies that are not exactly corresponding to the difference between two energy levels in their vibration modes. So let's see, what are these two mechanisms that broaden the frequencies that can be absorbed? The first and more important mechanism is referred to as pressure broadening, pressure or collisional broadening. And the idea is this. Suppose you have a molecule, say CO2 water vapor, and it gets a photon with the wrong wavelength, the wrong frequency, then it won't be able to absorb it, and it will just be scattered, if you want. However, suppose that we have a higher pressure in the atmosphere, so higher pressure means more molecules. So there's a certain probability that while the photon is absorbed, the photon with the wrong frequency, another molecule hits our molecule at the same time. So what will happen in this case is this photon would be able to be absorbed by this. Only the right part of the energy there would be absorbed from this photon, and the excess energy would be transferred to this other molecule as kinetic energy. So this allows us to absorb a photon even though it doesn't have the right frequency, the right energy. Because it can either release some energy or get some energy from the collision with the other molecule. That happens only if the collision happened together with the absorption, and that happens only if there are enough molecules in the atmosphere that keep colliding, and therefore that happens at a high pressure, and that's why it's called pressure broadening. Once the molecule absorbed the photon, it's now vibrating stronger. But remember, the atmosphere is also releasing long-wave radiation, so these CO2 or water vapor molecules can also release these photons. So then we are sitting at this energy right here. We release a photon and we go down to this one, or we go down to this one, and we release these other long-wave photons. We could be releasing them either upward or downward, depending on how the molecule is arranged at a certain moment. And then the vibrations becomes less energetic, and the photon is released back into the atmosphere. Okay. So now we understand that the photon can be absorbed even if it doesn't have exactly the right energy. Of course, it's limited by these other collisions. So if it does have the right energy, that helps a lot. And also, it's only a small correction that this can help us with. But still, it's important that the photon has the right energy. For example, the photon needs to be in the wavelength that is roughly that absorbed by CO2 and so on. The other effect that allows broadening, which is less important in the Earth atmosphere, is this. So a molecule can also absorb a photon of the so-called wrong frequency due to the fact that it moves. So you remember the Doppler effect? You're standing here and the ambulance is approaching you. You hear it as a high frequency. You're standing here. You hear it as a lower frequency than what it really is. We all know about that, presumably. Okay, great. Think about the molecule is moving. When it's moving, it will see the frequency of photons different from what they actually are because of the movement of the molecule. So it would seem, so if the photon is at the wrong frequency, it would seem to have a different frequency because of the motion of the molecule, and then it might see it as having the right frequency, and then it can absorb it. So in the Earth atmosphere, this is a significantly weaker effect, but it also allows molecules to absorb photons that are not exactly don't exactly have the right energy to transfer the energy, the molecule between two energy levels. So now that we understand absorption by CO2 a bit better, let's go and look at this again and try to understand what we're seeing. So we said that this line right here is the long wave radiation of a black body at a temperature of 287, and we see this hole here. Notice that the hole in the absorption, so this is the radiation at the top of the atmosphere, that is seen at the top of the atmosphere, seen as the wavelength, or wave number in this case. Again, wave number 1 over wavelength. You see that the emission here in the CO2 window is at a temperature of 220. This is the temperature at the emission height, right? We see that in this window, the temperature that corresponds to this emission level corresponds to 220 Kelvin, so minus 50 something Celsius. And that is because at the emission height, this would be the temperature. At the emission height for CO2, the temperature is very cold, and therefore the radiation we see at the top of the atmosphere, that's what this is actually a radiation corresponding to very cold temperatures because it's not emitted by the surface at this wavelength. It's actually emitted at a height of a few kilometers after being absorbed and released and absorbed and released a few times, and then finally released from the emission height. So you see that the emission height actually depends on wavelength. It's not a simple emission height. In one of the workshops, you'll be asked to calculate what is the effective emission height. It would be sort of an average. But you see that the emission height in the ozone window is 260 Kelvin, so that's a certain height, while for CO2 it's 220, so that's much higher in the atmosphere. Remember, the atmosphere gets colder as you go up in the troposphere. The question we're asking right now is this. When we double the CO2 and then double it again, how would that affect the radiative forcing, the amount of heat that is being trapped in the atmosphere by the excess CO2? Let's start with so the subject is logarithmic dependence. So let's first consider a case that is not like the atmosphere. Suppose we have a pipe. The distance along the pipe is x, and there's a certain radiation that comes here into the pipe. The radiation initially is I0, and then it's absorbed in the pipe and decays, and we get a weaker radiation coming out of here. And we're asking, what is the radiation intensity along the pipe? So here's a small section of the pipe that is dx long. We have a certain radiation coming into it and another radiation going into it. So the radiation absorbed here, di, that's what absorbed, is equal to minus mu I dx. That is, the absorbed radiation is proportional to the intensity itself and the distance in which the radiation is absorbed, and mu is some proportionality constant that depends on the gas or medium and so on. So now I can divide by dx, and I get that di dx is equal to mu minus mu times I. Does anyone remember what the solution for this would be? Again? Yeah. So it's going to be I0, the initial one, times e to the minus mu x. So we're going to get an exponential decay. Okay. So when you think about increasing the concentration of gas here, you see that this would lead to an exponential decay and so on. So when you think about absorption, typically you think about it as depending exponentially on the absorbing medium. It turns out that that's not the case for CO2. What happens with CO2 is a bit different. The radiative forcing, so for CO2 in the atmosphere, we can think about the radiative forcing as being proportional to the log of CO2. Say log 2. Would make it easier for us in a second. And as a result of that, the warming that we get is also going to be proportional to the log of CO2. So we can schematically write the following. We have delta T, the warming, is equal to some amplitude A times log 2 of CO2 divided by 280, which is the pre-industrial ppm. 280 is the pre-industrial CO2 concentration. So if CO2 is equal to 280, this is just 1, and log of 1 is 0. So there's no warming. But if the CO2 is higher, this is how the warming will depend on the CO2. This is sort of an empirical relation that holds pretty well. So if CO2 is equal to 2 times 280 ppm, then delta T is equal to A times log 2. What's this? 1. So that's equal to A. So therefore, A is equal to the warming that would occur for a doubling of CO2. So here comes the surprising consequence of this, which is what people are typically not aware of. So I could write the temperature itself as function of CO2. I could write in the following way. There would be the initial temperature plus this A log 2 CO2 divided by 280. Okay? So now I could ask, suppose I double the CO2 and then I double it again. What would be the warming? So suppose the warming due to one doubling is A. Say A is 3 degrees. What do you think would happen? So if I go from 280 to 560 ppm, then the warming is, say, 3 degrees Celsius. What do you think the warming would be if I go from 560 to 1120 ppm? You would think 6. Say again?
Like 4.5.
4.5. So let's see. Let's calculate this and see. Okay? The answer is that this would also be 3 degrees C. Strangely enough. So even though you're adding 560 and here you added only 280, the warming is the same warming. That is the importance of this logarithmic dependence. So let's see how that works. It's like a two line derivation. So we have T of 2 times CO2. That's the temperature at 2 times CO2 minus the temperature of 1 times CO2 is equal to A log 2 of 2 CO2 divided by 280 minus A log 2 of CO2 divided by 280. That's equal to A log 2 of 2, which is equal to A. And then if I look at the second doubling, so now I have the temperature at 4 times CO2 minus the temperature at 2 times CO2 is equal to A log 2 of 4 times CO2 divided by 280 minus A log 2 of 2 times CO2 divided by 280. That's again A log 2 of 2, which is again equal to A. Yeah, subtraction outside, division inside. So if I have, it's all multiplied by A, so I take the A out. I have this log minus this log is equal to the ratio of the arguments, and therefore all I'm left with is this 2 factor here. Does that make sense? And similarly here, all I'm left with is 4 divided by 2, and that's why this happens. So I've used the property of logarithms that when you take the difference of logarithm, it's the log of the ratio. That looks like everyone is nodding, hopefully. Okay. So it's surprising that when you increase the CO2 by 500 ppm, you get the same warming as you got by increasing the CO2 from 280 to 560. Okay? So that's logarithmic dependent. So again, I just wanted to emphasize this. The surprising result is that if we increase the CO2 from 280 to 560, so that might happen when? We're pretty close to 560 now. We're at 420. If you take into account all the other gases, the methane and so on, we're actually close to 500 right now. We're pretty close to 560. The only thing we need to do is wait for the climate system to adjust to the new CO2. That takes time. But if we just leave the CO2 as it is now and wait, we're pretty close to doubling. By the end of this century, we're likely to get there, or you're likely to get there, not we. And then that would be another, if this would be 3 degrees, this would give us another 3 degrees. Okay, so the last thing we want to talk about is comparison between CO2 and other greenhouse gases. There are other greenhouse gases, like methane, for example. And methane per kilogram absorbs a different amount of radiation than CO2. The difference is that methane has a very short lifetime in the atmosphere. So if you release a kilogram of methane, it absorbs more initially, but it decays out very rapidly into CO2 mostly. And as a result of that, you can't just take the absorption by a kilogram of methane. You have to take into account the fact that it decays rapidly. Okay? So this is the reason for defining the global warming potential of a certain gas. So think about it in the following way. We have a certain time horizon. TH would be, say, 20 years or 100 years. We're asking how important is an additional kilogram of methane in the atmosphere relative to an additional kilogram of CO2 in terms of the radiative forcing. So AX would be the radiative forcing per 1 kilogram of methane, say, and this one would be the same thing for CO2. So R of T is the decay rate of CO2. It hardly decays on a short time scale of decades, while methane decays rapidly. So this is the decay rate of methane, which has roughly a lifetime of 12 years in the atmosphere. And so what we're calculating is this is the effect of 1 kilogram of methane, but this is the decay in time of methane, and we're integrating this from 0 to, say, 20 years, and we're finding what is the total effect of methane on the radiative forcing, and are dividing this by the similar effect of CO2, and this allows us to compare the effect of methane to CO2, even though methane decays rapidly and CO2 does not. So this is a tool for allowing us to compare the effects of different greenhouse gases with different lifetime in the atmosphere. Here's the bottom line from Wikipedia. So the lifetime of methane is 12 years. The global warming potential is 86 for 20 years. That means that if you release now a kilogram of methane, it's 86 times more powerful in terms of a greenhouse gas than CO2. If you check that over 100 years, during which much of the methane decayed and turned into CO2, it's only 34 times more efficient, but still much more efficient. The quantities of methane in the atmosphere are much lower than of CO2, so therefore this balances the fact that methane is much, much more effective as a greenhouse gas. And you can see other greenhouse gases that can be very effective, but their concentration is very low. So still, CO2 is the major greenhouse gas because its concentration is high, even though there are others that are much more effective. You remember that in the movie, The Great Swindle of Global Warming that we've watched in the first class, they said that water vapor is a much more effective greenhouse gas than CO2. That is correct. We saw in the outgoing long wave radiation curves that H2O had an effect on the emission at certain wave numbers, wavelengths that CO2 did not. It turns out the fact that water vapor is a more effective greenhouse gas is actually bad news for the following reason, and that is the water vapor feedback. So suppose we're increasing CO2. This leads to a warming of the atmosphere and the ocean. If the atmosphere is warmer, it can hold more moisture due to the Clausius-Clapeyron relation that we saw in the last class. So warmer air can keep more moisture. That means that the greenhouse effect of the water vapor is higher, so more water vapor in the atmosphere, more absorption by water vapor, and therefore more warming. So in fact, the water vapor acts to amplify the effects of the CO2. Half of the warming that we are seeing due to CO2 is because of this amplifying effect of water vapor in the atmosphere, and only half the direct effect of CO2, roughly. Okay? This is a feedback, right? Because we're increasing the CO2 and causing warming. Now there's feedback on the warming. Let's understand why this is a feedback. We have a certain warming. This increases the water vapor, increases the greenhouse gas due to water vapor, and causes additional warming. So that's a feedback mechanism. What will stop this feedback? The fact that as the atmosphere warms up, there's more and more black body cooling, black body radiation out of the atmosphere that prevents it from cooling, and eventually that would stop the warming in spite of this positive feedback. So positive feedbacks in climate are very important, and this is the ultimate example. Okay, let's conclude. First talked about the energy balance of the atmosphere, and we calculated the surface temperature due to this balance of the incoming shortwave radiation being equal to the outgoing longwave radiation. That gave us a very cold temperature for the surface of the Earth that didn't make sense, and then we added the atmospheric layer, which traps some of the long-wave radiation and therefore leads to warming. That is the natural greenhouse effect due to the existence of an atmosphere. This isn't the greenhouse effect of anthropogenic increase in CO2. Then we mentioned the fact that every photon of long-wave radiation that can be absorbed by CO2 and is released by the surface is already today absorbed, or even before the Industrial Revolution, is absorbed by the atmosphere. So the effect of CO2, the additional CO2 that we're adding, is not through changes of how many of these photons are trapped, but due to the change in emission height that we discussed. So the increase in emission height and a couple of other effects leads to this warming that we're seeing due to the increases of CO2. And CO2, we didn't mention this, but CO2 is especially effective because it actually traps radiation at wavelengths that are not trapped by water vapor. So they complement each other very nicely. Here, let me show you the relevant picture. So this is wavelength of the long wave radiation. And these are the bands in which things are being absorbed. So you can see water vapor is absorbing here and is absorbing here and not all of these places. CO2 is absorbing here. And that happens in this window where the water vapor is not absorbing. So in this wavelength range, water vapor is less effective, and this is where CO2 is more effective, so they complement each other. It's not that water vapor is not effective. It's very effective. Look how much gray thing here, which indicates absorption. It's just that in this particular window where CO2 is absorbing, water vapor is a bit less effective, and that's why CO2 is such a powerful greenhouse, because it complements the absorption by H2O. This is an important one. That's the logarithmic dependence. So every doubling of CO2 leads to the same warming. If one doubling leads to 3 degrees, the next doubling would also leads to 3 degrees. In a sense, that's good news because we might get to the second doubling, and if this were linear, it would be much worse, so at least it's logarithmic. We talked about the positive feedback due to water vapor in the atmosphere, the ultimate example of a positive feedback in the climate system. And we talked about the global warming potential, which is a way of comparing different greenhouse gases. And as I mentioned before, if you take into account all greenhouse gases, there's a concept of equivalent CO2 mixing ratio, which is the equivalent CO2 concentration that is equivalent to all of the greenhouse gases. Today we're roughly at 500, if I remember correctly. So even though CO2 is only 420 parts per million, remember it used to be 280 before the Industrial Revolution. We're actually at 500. 560 is doubling. We're pretty close to doubling, so we'll see doubling soon. What saves us from the warming that's expecting is the finite